All right, so hello everybody on Zoom, hello everybody on the lecture hall. Today is going to be the last week in which we're actually going to have material of the course. Next week, we are going to have mostly a wrap-up. I'll go over what we have learned during the semester. We'll probably have a quiz game, a little bit like this 1 against 100, Eis gegen 100. In Swiss German, and then you'll compete. There will be you, there will be the TAs. I'll try to make it work, that it both works from the lecture hall and from Zoom, that everybody can participate. Yes, so that will be the end of the semester. But today, I have one more thing to show you. That is actually pretty cool. It's also master's level. I mean, I warned you that we are already done with the bachelor's level part of the lecture. Which stopped with evaluation. And we started one master's level topic, which was probabilistic information retrieval. How hard was that last week? Who found it difficult? Okay, yeah, it was a bit more involved, right? And I assume on Zoom, how did you find it last week? Was it difficult? Was it easy? Was it a walk in the park? Anybody on Zoom can say in the chat. Okay, nobody wants to assess how it was. Okay, so, but I assume that it was not easy, right? Because we used the Bayesian rule. We used a lot of complex math. I hope that I still managed to demystify it a bit, you know, to show that in the end we are just deriving formulas. But a few interesting things happened at the end, because we derived from this model based on random variables by ranking the documents by the probability of relevance decreasing. We wrote down the formula, we derived stuff, and we noticed two things at the end. The first thing was it's pretty much a weight/dot product based model that is very easy to implement because it works pretty much like what we've done in vector space models, right? You just walk through the standard inverted index, document by document, and you just accumulate scores by adding. So it's pretty much just addition and multiplication. So that was actually great because it means it's easy to implement. You can just almost reuse the same code, but of course, the only thing that changed are the weights. The second thing we noticed is that by making a few assumptions that I agree with you can sometimes be a bit, let's call them courageous, we landed on the inverted document frequency, right, the IDF. So that alone gave a justification for the use of IDFs in the weights. So now you know, you can say, why do we use IDFs? Well, this can be justified by probabilistic models that we use the IDF. But there is one thing that we didn't see in the probabilistic model, and that's the term frequencies. This we didn't see. So we still need to justify where these term frequencies come from. Why do they make sense to have as in the weighting system? It turns out we're going to have them today. This is one of the surprises. It's not going to be a surprise because I've already told you, right? But today's surprise is going to be that somehow the term frequencies will pop up just like a rabbit out of a hat from these models right here. And then you know, okay, this is why we have term frequencies. It's because of language models. And this is why we have inverted document frequencies. It's because of the probabilistic-based models. There is something else that I wanted to say about these assumptions that we are making, because the assumptions were sometimes very pushy. But what happens is that if you test the system, if you actually implement the system and make it used by people and use this evaluation matrix that we've defined 2 weeks ago, it works well. So it turns out that making these assumptions that you could criticize and, you know, think like these are not good assumptions, yes, but the system works. So in the end, this is what matters, right? So this is why these things actually became quite popular. All right, but enough said. I mean, now this is the appetizer. So now I might as well get started. It might be that today, as you notice, well, those in the lecture hall notice that the number of slides is lower than usual. So it might be that I'm even going to be done in less than 2 hours. So we're going to have some of your time back, but let's see if we manage. There is something that you probably saw already, I assume, in theoretical computer science. Who already saw something like that? Almost everybody, right? Also on Zoom? Who has ever seen something like this? Okay, lots of raised hands. Perfect. So you're familiar with that. This is a finite state automaton, right? All right, so the way it works is that we have this, it's like a video game in a way, like this. Anyway, so there's a start right there. And then we have what are called transitions, in that case with A and B, and then you see this rectangle that's called the final state. Anyway, but let's just use it. So we usually have what's called a transition table, but it's pretty much the same. It's kind of redundant with what is showing right there, right? Because, for example, you see that if I call it state 1, so this is the state right there, what happens is that if I use the transition that I see the letter A, I go to the green one. So the letter A gives me to brings me to number 5. So I don't have the numbers in there, right? But that's 1, 2, 3, 4, 5. So you see, this is the state transition table. And at every state, I go to the next state by looking at the letter that I'm consuming, right? It's actually not very far away from a Turing machine, right? It's kind of a simpler version, but it's a machine. It's also the machines that we love to draw on screens. I mean, it's not something we have in our hands, but we can do these beautiful diagrams. So let's try. Let's have this input right there, BAAAA. That's it's called a word, right? So it's made of letters, BAAAA. And we are just going to follow the rules right there and starting right here. So I put in yellow where we are right now. So can anybody tell me where we go next? Just checking, you're supposed to know that, right? So where do we go next if we consume B? Yes? To the right, yes, exactly. There you go. So you see, I move along the little cursor right there. So you see, I just move it here. We consume the letter B, and of course, we followed the transition for B. Then I'm consuming the letter A. Where am I going next? Yes? Also to the right. So you see, then again to the right. And then you see there is this cycle right there. So A, and then I stay here. And then I notice that I am within that rectangle here that says accept. What does it mean with accept? Well, it means that after doing all of this thing, which is nothing else than an algorithm, we determine, based on the fact that the final state we are in is within this rectangle right there, the set of final states, we accept that word. Accept as what? Accept as belonging to the language that this automaton is describing, right? So an example of word that does not belong to the language is this one. So I start here, then I follow B, A, B, A. And then you see I'm not in the rectangle, so this is rejected. This word is not part of the language, all right? This is actually, of course, then you can, I don't know if there actually are computer science departments who have entire research groups dedicated to finite state automaton engineering, but this is basically called a sink in terms of design, right? So you have a node that then has all the letters stay on it. That's not part of the final state. That's called the sink. So it's a way of saying, okay, whenever you land here, you just stop like that. It's like a black hole of finite state automaton. Okay, so we had one example of acceptance, one example of rejection. Formally, the way that worked is that you have a set of states, you call them Q0, Q1, and so on all the way. So here I start with 0 instead of 1, but you get the idea. I have a set that's my alphabet, right? I call it sigma, so it has all the letters in there. I have a set of final states that is a subset of all the states. Q, I think that's intended to be. And then you have this delta function, that's the transition function, that takes the prior state and the letter that is consumed and returns the next state, right? So this delta function is just this transition table is there, is the delta function. Okay, but this is all things that you've studied, right? It's a finite state automaton. Of course, there's plenty of variations of that. Then you have the undeterministic version where you can have multiple lights at the same time all over the place. You have some automaton that can have memory, and so on and so on and so on. All right. But anyway, the whole theory behind this is that we can build automata like that, and they are always associated with a language that's just the set of the words that they accept, that we can call L. And so when you have a language like that, under certain conditions, you can build an automaton that recognizes words in that language. By the way, anybody gives me a characterization of the language that is accepted by this automaton in any form you want? Maybe on Zoom. Let me see if anybody on Zoom knows. Okay, any idea? Yes? Yes, so this is like the English way of putting it. So an input that starts with a B, I'm repeating in the microphone, and then with at least 2 A's or more A's. Is there a more formal characterization you could give me, like as a formula? Anybody? Does the term regular expression ring a bell? Yeah. So you could say BAA A star, right? Or BAA plus. So it turns out that there is an equivalence between regular expressions and automatons. So you have this whole theoretical computer science dedicated to this, where you have the sets of the languages, and you have classes of languages, and then you have this whole equivalence with the ones that are regular expressions, then you have context-free grammars, and so on. So you have all kinds of levels for that. All right. But anyway, we have this language space. So what we are going to do in the context of information retrieval is that the letters in that language space, they are not going to be just A and B. These are going to be the terms that we have in our books. These are actually going to be words instead of the letters. So what's more, we are going to do something in addition to it. I'm changing that to omega, and then you might smell the probabilities coming in right there, because in fact, we can indeed start introducing some measure on the set on that language of the accepted words. And we can assign probabilities. So then each word is an elementary event, right? And you can associate each word with a probability. Now, if I want to formulate it in terms of information retrieval, I shouldn't say word and letter. I should say a document and term. So basically, it means that the language contains documents. The documents are sequences of terms, lists of terms, and I assign every document a probability. So I call the documents omega, and the probabilities of the documents can sum up to 1. Another way of putting it is that as omega, you can take the set of absolutely all possible documents, and you just put a probability of 0 to those that do not belong to your language, right? But what happens is pretty much this. So now I switch back to L instead of omega, right, to come back in the ID. But basically, I have here my language space. I have a probability assigned to every element of that space that sums up to 1. And we see again, my language space is going to be a set of documents, and the documents will be lists of terms. All right. So now, if we come back here, now that we have added this probability distribution, which we didn't have until now, the question is, how can I tweak the things in there in order to turn it into a generator of words? Because right now we used it as a detector, right? You feed a word in, and then you press the button and see how the light moves and see if it lands in the final state. So this is a detector of words. How can we now generate words of the language? Yes? Ah, yes, that I didn't think of. Yes, indeed. So you could start with a final state and then go the other way around. Then you would, with guarantee, produce a word that works. But then another important part is what you said, I'm assuming, is that you follow the arrows, right? You traverse the rows of the graph. But the thing is, if you do it that way, you still have to land on a starting state, right? So you could do it that way. It would be equivalent. But the key thing in what you said is you follow the arrows. You basically just walk in the graph. If we want to even formalize this a little bit, and given that we have a probability distribution, we could introduce these weights right there, that at every state, I can say, like in the starting state, for example, in the starting state, I can have a probability of 1/2 of following B and a probability of 1/2 of following A, right? And of course, I'm assuming that the probabilities of the outgoing arrows, they sum to 1, right? So I basically flip a coin and I go here or I go there, right? And then if I do that, then you see, yes, so let's light that up and let's toss a coin like this, or maybe you can use dice. It's the same. So here, let's say we have generated a random number that leads us there, and then here, and then here. Oh, we were lucky now. Well, maybe I can continue a bit, but basically I'm in a final state. So now what's happened is that I have generated this word, BAAA. The probability that I would generate that word is pretty much 1/64, right? Because I just, what I did is that I multiplied the numbers, 1/2 times 1/2 times 1/2, and so on and so on and so on, right? All right. So this is pretty much the tweak that we do to our system, and we just make sure that we arrive, of course, in a final state right there. But this is pretty much the idea. Is that clear? What's going on here? Right. So we just start on a starting state. We follow the arrow by just tossing coins or throwing dice until we land on a final state. Then we can even continue if it has loops upon itself, and then at some point we decide to stop. So it means that in order to stop, I can also do that with probabilities. So here I can say, okay, with a probability of 1/4, I'm actually going to stop right there. Okay. So what happened is that I generated a document at random. Remember how last week the documents were random variables, right? This big D, this uppercase D, that was a random variable that as a value takes a document. Well, today it's also going to be the same. The only difference between today and what we did last week is that last week for the probabilistic information retrieval, what was our model? Set of words, bag of words, or list of words? Yes? Set of words, exactly. It means we had Booleans, vectors of Booleans, so either a term belongs to a document or it doesn't. But what I showed right here, what model is that? If I say that a document is a sequence of terms, right? With this abstraction, the one I showed earlier, with this abstraction right here, like this is a term, this is a term, this is a term, and that's the set of documents. What is the abstraction here? Yes? List of words, exactly. So we had set of words last week, and now we have list of words. All right. So this means now that formally, I have a random variable that takes its values in T star. So T star is borrowed from this monoid structure stuff, where this is a clean star that basically means it's just a sequence of terms of arbitrary length, right? You know this whole monoid with concatenation and so on, right? You've done that? Maybe not. It's very easy, let me tell you. So a monoid is just a mathematical structure that has a concatenation operator. So it basically you can have a set of terms. And then whenever you have an element of the set and an element of the set, you can concatenate them. First this, then that, and then it's stable. So you obtain again an element of the set. It has a neutral element. What is the neutral element of concatenation? The empty string, exactly. It's very often called epsilon. And so you have a neutral element, the empty string, that leaves it unchanged. And basically, when you do that, the notation for that set is with a little star, right? So if it's basically the set of arbitrary length sequences obtained from a given alphabet. So if the set of terms, all the terms that we can see in a book are in the set T, then T star is basically the set with all the possible lists of words that I can have. Right? Is that clear? Right. So it's really just a notation. Don't be scared by notation. This is just telling you, okay, that's just the set of all lists of words that I can ever generate if I take my words in T. Why did I put omega a row here? Can anybody tell me that? Checking your understanding of the formalism. Yes? Exactly, it's a random variable, and we saw that a random variable, in fact, is not a variable. That's actually a poor name, but this is what it's called. A random variable is a function from an omega space to any set, right? And then it's like I said, when you ride a bicycle and throw away the little wheels, at some point you forget about the omega space and just consider the random variable itself. So what many people do is that they forget that part, and they just say, okay, we have a random variable in there. But the random variable always comes from an omega space that is implicit. All right, so indeed, this is because it's a random variable. Okay, so it is indeed the list of words model. So this is different from last week. Last week, set of words, this week, list of words. And of course, when you have a random variable, you can take functions on random variables, right? So in particular, if I have a random variable L that has values lists of words, I can take the length of the documents. So I can use this notation with the double bar, which is some kind of norm. That is a random variable that gives me the length, the number of words in the list of the documents. And now it's a random variable that is an integer, right? Still omega 2 because it's a random variable, but basically it's an integer, a natural integer, right? So 0 if it's empty, 1 if it's just one word, 2 if it's 2 words, and so on and so on. So I can also consider this as a random variable. And we'll see that this is actually also going to play a role in our model, the length of the documents. All right, so now what's going to happen is this. We have this collection of documents. Let's say it's the ETH library with, I don't know, 1 million different books. And we can pick the books in that library, and given these books, we can generate models like that. So we can pick a book, generate a model, pick another book, generate a model, pick another book, and generate a model. And the idea, oh, sorry, not yet. The idea, it's actually something quite fun. And actually, I was playing with that as a teenager because there was this cool stuff over the internet that you could play with. You can basically take a book like, say, Sherlock Holmes, transform it into a language model, and this language model can then be used to generate new Sherlock Holmes, right? So then you can play, you can do it with music too. You can feed with Bach music, and then you can ask the system just by pushing the buttons to just generate more music like that. So it's actually pretty cool to do, and there's even an exercise that you'll have to actually do that. And you can actually generate plenty of new documents just out of these models. And so we'll study how this actually happens and how we derive these models from the documents, and how we'll turn this into an information retrieval system, which is the main insight of today. All right, so far so good. Is everybody following? Yes? Okay, on Zoom too? A few raise hands on Zoom. Yes, perfect. Few raise hands. Awesome. So everybody's following. Okay, now don't be scared. Let me throw a formula at you. Here you go. Don't be scared. It's really easier than it seems. This is just the chain rule. Remember, the chain rule is when you say, okay, you have probability of A, and then you multiply that with the probability of B conditioned on A, and what you get is the probability of P of A times P of B conditioned on A gives me. You can write on the Zoom chat too. The chain rule, anybody? Wrong answers are totally okay. It's always fine with me. You can also try. The probability of A multiplied with the probability of B conditioned on A. Yes? Yes, exactly. That's the probability of B and A. And this is called the chain rule, because whenever you want to compute the probability of B and A, you can write it in that way. So you can say, okay, the probability of B and A is the probability of A times the probability of B conditioned on A. But the cool thing is that it also works if you have, let's say, 3 of them. The probability of A, B, C, no problem. It's the probability of A times the probability of B given A times the probability of C given B and A. So you can do it with 3, with 10. I'm not going to do that to you with 10, but this is pretty much the idea. So what's going on here? Well, that's pretty much the same thing, right? I'm using the chain rule. So I have, what I'm trying to compute here is the probability that I'm generating this document right there. It's a document of length 3 with 3 words, D1, D2, D3. Of course, I could have written, I don't know, information, retrieval, computer, whatever in there. I just call them D1, D2, D3, right? But you can put anything in there. But basically, it's the probability that the value of that random variable is this document with 3 words in that order, because it's a list of word model, right? So what is the probability that I generate exactly document D1, D2, D3? We use the chain rule. Let's decompose that into a conjunction of events. What does it mean that I have a document on length 3? It means that I have a document of length at least 1, and the first letter is D1, and I have a document of length at least 2, and the second word is D2, and I have a document of length at least 3, and the document is D3, and the length is exactly 3, right? So this is just what I said is just another way of explaining this D equals D1, D2, D3. Do you agree with that? It's exactly the same thing, except that now I've expressed this as a conjunction, this and this and this and this and this. So now that I have a conjunction, I can use the chain rule and express that's purely mathematical or mechanical, and I just go ahead with the chain rule. So what did I start with? Well, first, we must have the length of D. I use LD. I could have used this double bar. Maybe I can simplify the notation later. But anyway, the probability that the length of document D is at least 1. Multiply with the probability that the first term is D1. D1 is just a notation for the random variable with the first term, right? So the probability that the first term is D1 conditioned on the length being at least 1, conditioned on that. What is this product? Exactly. It's the probability that the length is greater than 1 and that the first term is D1. Okay. And then I continue with the chain. Now that I have this conjunction, so this is basically what you just said is right here, right? We know that the length is at least 1 and this is a little n, right, in logic, and that the first term is D1. Now we have the next conjunction in our list where we want the length to be at least 2. Right? So this is the probability that the length is at least 2, given that it's at least 1 and that the first one is D1. And so if I multiply this and this and now this, what I get is, if I multiply these first 3 factors, yes? Exactly. So if I multiply these 3, it's the conjunction of these 3 things. So now it's the length is at least 2 and the first term is D1, right? Which is basically written here as the next condition. This is how the chain rule works. So now that I have this conjunction, I know the length is at least 2 and the first term was D1. I compute the conditional probability that now my second term is D2, given that the length was 2 and the first term was D1. So now I have the conjunction that, you guessed it, that the length is at least 2 and the first term is D1 and the second term is D2. Next in the chain, the length is at least 3, right? So now I have the conjunction that the length is at least 3 and the first is D1 and the second is D2. Next, I compute the conditional probability that the third term is D3. So now what I get is that the length is at least 3 and we have D1, D2, D3, which is my next condition in there, right? And then I compute the conditional probability. This is where it stops. The length is 3. It's not 4, it's not 5, it is 3. So you see, this is the chain rule that is just a decomposition of the fact that the document is D1, D2, D3. Is that clear to everybody? All right. Notice that this here is the decomposition when we have a list of words. Do you remember the decomposition when we had sets of words? How we decomposed it last week? Just reactivating your memory. It's called the binary independence model. Do you remember that? So the document is a vector of Booleans then. On Zoom, does anybody remember how the decomposition looked like for sets of words rather than lists of words? I look at my screen. Is there any lights that pops up for somebody who writes? No? Okay. Oh, there. Yes, go ahead. Yes, exactly. That's exactly the idea. So indeed, I'm repeating that what you said. You said it's similar to this, except that now the factor says the probability that D1 is contained because it's a set of words in the document and so on. Yes, absolutely. And more precisely, you might remember that it was a product over the terms. It was a product over the terms, and each factor was the probability that a term was or was not in the document. Was if it was a 1 and was not if it was a 0. Right. So you see, we've done it last week for sets of words. Now we've done it for lists of words, but that's pretty much the same idea. All right. So in that case, we use the chain rule. And by the way, here we don't need an assumption on the, there was an assumption last week, right? It was the binary independence model assumption. We assumed that the terms they were independent of each other, their occurrence. For now, there is no assumption here because this is just a chain rule. It's a theorem. It always works. All right. So now we can simplify a few things, of course, in our models. Because you might have noticed these, I nicely arranged them like left and right on every line. Basically, what the probabilities on the left of every line here on that slide express is basically the probability that it doesn't stop here. Right? Here it's the probability that we have at least one term. Here is the probability that given we have one term, we have at least a second one. Here it's the probability that given two terms, we have a third one. So this is the probability that it doesn't stop here. I can re-express it in that way. Now we can make an assumption. We can assume this is always the same value. That's part of our models, right? So we can assume that we have a specific probability of stopping or not stopping, right? And so if I decide to call p stop the probability of stopping, well, the probability of not stopping is 1 minus p stop. Right. So basically, this is 1 minus p stop, this is 1 minus p stop, and this is 1 minus p stop. And here, this is p stop. Right. How do you see this? Well, the probability that the length equals 3, given that, is exactly the complement within that set, of course, of the probability that the length is at least 4. Right? It's disjoint. Either it's 3 or it's 4 or more. So this is why it's p stop and 1 minus p stop. All right. So yeah, so 1 minus p stop, 1 minus p stop. That's a simplifying assumption. And here we'll come back to this later. It's basically every time the probability of the next term coming in, which will be the fun part. All right. Speaking of that, we'll make another simplifying assumption. Right. So we've simplified that. Let's simplify that. We are going to assume something that is called the Markov rule. Has anybody heard of Markov chains before? Who never heard of Markov chains? Okay. On Zoom, who never heard of Markov chains? Did everybody hear Markov chains on Zoom? Are you still awake on Zoom? Yes, okay. So we have a few people who never heard. Then I'll explain, of course, what a Markov chain is. So it has to do with the chain rule, actually. So we imagine that we have this conjunction of logic predicates, but we just don't have just one or two or three or even 10 or even 100. We have a super long stream of predicates. They just keep coming and coming and coming and coming. So we have a huge stream. And we have these probabilities right there that say, okay, the probability that, so that's the next predicate, the probability that the kth term is going to be decay, given what happened before. So I have, of course, the condition that we know there is a kth term. And here, these are the previous terms from the very beginning all the way to k minus 1. So we have this stream of words that just keep coming. And every time we compute the probability of the next one. What the Markov rule tells us is that the probability for the next term is only dependent on the immediate past, but not too far away in the past. It means that you can delete from D1, D2 all the way to k minus n minus 1. So you forget about the past, and you only look at the previous n terms. Let's call it n. Right? Then n is a parameter, can be 0, can be 1, can be 2, and so on. Right? But basically, the Markov rule says whatever happens now is only dependent on what happened in the previous minute, or in the previous week, or the previous year. Right? And everything else you forget. This is an independence assumption. This is saying that the kth term being decay or being something else is independent from anything that happened before that moment in time. So it's an independence assumption, just like last week with the binary independence assumption. For whom is that clear, the Markov rule? Right? Okay. So this is the Markov rule. And then we even call it, I'm not going to do it now, but this is called the Markov chain, where you actually invoke the random variables like this. It's very popular in stochastic things, stochastic research. I think also on the financial markets and so on, you have that sort of assumptions that you can use. But this is basically called the Markov rule. Why did I put in the title n+1 gram? We've already seen the k grams, right? 1 gram, big grams, 3 grams, and so on. These are basically windows of words, right? Well, it's the n+1 gram, because you have to imagine here these n terms plus the new one. So there are in total n+1 terms that we are looking at, the past n that we are looking at to condition on, and the new one. So this is why I call that an n+1 gram. But the idea that you should have is really this idea of a sliding window, that you keep generating new terms and you slide the window on which you condition, throwing away everything that's far away in the past. One way to put it is that it's kind of as if you have limited memory, right? You just keep forgetting what's too far away in the past, you forget about it. All right, so here is an example with 3 grams. It means that n equals 2, right? So if I only look at the previous 2 terms, then I'm looking at 3 grams. So now I'm redoing the same thing, this ugly formula that I showed you right here. I'm rewriting it now in the case of 3 grams and also using my assumption on p-stop. And this is what I get, right? So the probability, you can even interpret it as it goes as a stream of terms. The probability that the document is exactly a document of length 4 that has D1, D2, D3, D4 is first the probability that we don't stop right away, because of course, if we stop right now, we have the empty document, right? So it's the probability that we don't stop. And the next term, the first term is D1. Then you want the probability that condition on that we don't stop, multiplied by the probability that the next is D2, right? Given here, I'm using 3 grams, so I still remember that the previous one was D1. Then again, we don't stop because we need to go to D3, and then the probability of D3 given D1 and D2. I remember, right, because n equals 2, so I can remember 2. Times the probability that we still don't stop, so there's a fourth one, and that fourth one is D4, given that the second one was D2 and the third one was D3. Where is D1? Well, I forgot about it. I only have a memory of 2, right? So I forgot about D1. I'm only looking at 3 grams. So I have here, of course, when you start, you bootstrap, right? So D1, D1, D2, D1, D2, D3, and now D2, D3, D4, and D1 is gone. And finally, the probability that we stop. Who would be able to write that formula for every K and for every N? Okay, and on Zoom, please raise your hand if you feel capable of writing the same thing for any K and for any N. Okay, a few raised hands. Okay, try it as an exercise if you want. Right. Okay, so this is it. And the easiest to start with, I think it's soon going to be the break. Maybe I'm going to give you your break. What we'll do right after the break is called Unigrams. We are going to start with the simple case that n equals 0. What does that mean? Well, I don't even have any memory. I just keep forgetting everything, and I don't even know what the last term was. Right. So I just, select the next term, but doesn't depend on the previous one. These are called unigrams. Why do I have a specific section on unigrams rather than, talking generically about them? It's actually because for the purpose of information retrieval, unigrams are actually quite good actually already. Right. So it's already very, very powerful, even though, of course, you can go for bigrams, trigrams, and so on, and it works well. But unigram, we'll see that there is also a reason that I'm going to tell you after the break, why it is also treated in a very special way. All right, so let me not wait until it actually rings. Let me give you your break. So I'll see you at 3:15, as usual, and enjoy your break, get some fresh air, and then we'll continue with unigram models. And then I'll tell you how to turn that into an information retrieval system. Right, so I'll see you at 3:15.